Welcome to Topic 11, Measurement and Data Processing. This is the unit I usually start with first because it's relevant to both your exams and your experiments, your internal assessment, so you may be watching this more than once throughout the course. First lesson here is 11.1 Uncertainties and Errors in Measurements and Results. These are the objectives, and this is what I'll do first: errors and uncertainties. Firstly, the key terms. When you do some data taking, you may have a result like this. This here represents the true line, and if your values are always above that or always below that, or maybe doing a trend like this, you would say that that would be systemic error. So there is something wrong with the way it's being done. The random error would be values that still fit on the line of best fit, still give you the correct average, and are just to do with the way the instrument measures. So if they're close to the line of best fit, or they're close within each other, this is good. This is good precision. So that there has good precision, even though it has a systemic error. And if the values give you the value that is meant to be the line as best fit, that means it has good accuracy. So this has good accuracy and good precision. This one here has good accuracy but lower precision. This one here has good precision but poor accuracy. And you could also have poor precision and poor accuracy, which would be that. So going to some other diagrams, going to some other representations of that. Here we have a high precision because they're all falling in the same spot, but the accuracy is bad because it's a long way from the target. Here we have poor precision, but if we average them, they take us to the target. And this one here has both good precision and good accuracy. Now you will need to mention both the systemic and random error in your experiment, specifically mention those words. And you will also need to explain why they came about and how to solve them. So first of all, the most important thing is recognizing what they are. So here we have a systemic error because there is a fault in the thermometer, there are gas bubbles. So that will give you a consistently higher reading than you should. Or maybe if you're reading this down here and didn't realize there was a small bubble up the very top, that's going to give you a consistently lower value. So leakages in the syringe are other examples of physical errors in the measuring device. Another problem would be parallax errors. If you're reading the meniscus from up here, you're going to think the reading's here. If you're reading it from here, you will think the reading was much lower. So that is a problem. Another error with reading from these measuring cylinders is, first of all, in IB you are not using a measuring cylinder. You must use the expensive analytical glassware because it is far more accurate. And if you are, make sure you are using it to the most relevant levels. So if you're measuring, say, 1 mil, so that's 1 mil here, don't use this, which is a 10, so this is a 10 mil measure volumetric pipette. Use a 1 mil volumetric pipette because it's far more accurate, so your precision will improve. Lastly here, just to illustrate how important this is, just a 5-degree change in temperature here. Let's say it's 10-degree change because it's easier to read on here, which is still relevant for summer and winter in the room if the air conditioning's on or off. More realistically, 20 and 25 are definite values. You can see it's quite exponential here. So there's a massive difference in vapor pressure and evaporation rates, and that will influence reaction rate experiments as well. So there are these tiny changes in temperature are actually quite significant to your reactions, and that can include just people walking by with wind. That can alter the accuracy of balances and so forth. So you need to be, that would give you some random error depending on how the experiment does and the experiment works. That could also give you some systemic error. So you need to do a good analysis on what type of error it is and say the words systemic and random error and explain them. Inherent in your methods, and this will be tested for both in the exams and deeply entrenched in your actual experiments, make sure you have a repetition of 3. You can get away with 2 if it is an extremely precise measuring instrument, but 3 ensures that we have a good idea of the precision. And the range of 5 is necessary to get a relationship. So if it's like this, we're not quite sure if it's going to do this, we're not quite sure if it's going to do this. Is it going to be a straight line, or is it going to be this? So you can go above 5 if you want, but generally the magic numbers are 3, 5, repetition of 3, range of 5. So here are the rules for determining what the uncertainty of the instrument is. For the instruments you'll be using in general, you just take the smallest increment and halve it, and make sure you do that. And for the digital instruments, that's just the smallest digit. So let's go through some examples here. So here we have a measuring cylinder, which you're not going to use, but it's easy to see these values. This value here is 17 and this is 18. So you need to make the decision, is this value closer to 17.5, 17 or 18? And here I've chosen this one specifically because it seems the clearest at 17.5. So then you take the smallest increment, which is 1, and you halve that. So the uncertainty is 0.5. So the final answer is not 17.0 plus or minus 0.5, although that would be acceptable. And 18.0 plus or minus 0.5 is acceptable also. That would give you the range that would cover this value. But the best answer is 17.5 plus or minus 0.5. It's all about telling the truth. You don't know what the value is, but by saying it's within this range, you are saying the truth is within this range. So it's a way of seeking truth. It's the scientific method. Here is another problem. Stop the video and see if you can get the right answer. Okay, just here we have 1.6 and 1.7 here. So again, I've done this one on purpose. I've tried to make it closer to the middle so that I could test out whether you're really doing the 0.05s, because the smallest increment 0.1 here. And so the final answer you should have got is 1.65 plus or minus 0.05. If you did go for the 1.6 and 1.7, make sure in your data tables and in your graphs you've got the 0 there to show the accuracy that you measured at. Now try to do this problem. Pause the video. So here are your options. Hopefully your answer came up with the correct one, which is number 1. Here we have a digital instrument. So what you do is you just take the smallest digit and that will be your uncertainty. Now the flaw with all these machines is sometimes there's a reading on the side, and that goes for the glassware as well, and they will tell you what the error of the instrument is. That will override what we're learning now about how to work out uncertainties. So the answer for this one, just pause the video and have a choice, and hopefully you picked number 3. Just to make life a little bit harder for you still, there's something that's called the halfway method. Now in science we're seeking the truth, so it could be that the instrument is not actually the thing causing the uncertainty, and there maybe other factors such as this, where you are out in the field, there's this wind that you can't stop and it keeps on brushing against the balance and making your numbers jump up and down. So if you have a careful look at your values and analyze whether you think which one is more significant. So this is for huge uncertainties that override your instrumentation, and you have to make a judgment for that. So let's have a look at an example. Here we have a very accurate instrument, measures to plus or minus 0.01, but these are the readings you got. Now you can see very clearly, you might not be able to see it with some other data that you've done, so you may have to do both of these, consider both of these methods and say which one you chose. But you can see here there's massive jumps here, and so the precision is not really plus or minus 0.1. So it's clear here we need to do the halfway method. So what we do here is, first of all, we get an average. This average is 9. You'll have to trust me on that, or add it yourself. Then you then find which one's the highest value and which one's the lowest value, and then you halve that, and that will be your uncertainty. So here you have plus or minus 9 plus or minus 0.3, very different to what you would have got otherwise. You would have got 9 plus or minus 0.01 and reported that, but that, 9.00 plus or minus 0.1. It's all about telling the truth. That is really a lie. Your readings weren't really that accurate. That's indicating that you were getting readings that were like 9.01, 9.00, 8.99, and you really weren't. You were getting numbers that were jumping all over the place, which is represented here. So the halfway method allows you to tell the truth on the uncertainty here. When you're doing your equations throughout the entire course and when you're doing your experiments and internal assessment, you'll need to judge how many digits to report your final answer in order to tell the truth again. So you need to know what significant numbers are, which I'm assuming you know, except for zeros. People seem to have trouble with zeros. So just a quick overview on when to include a zero as a significant figure. If it's in between a list of numbers, you count it. If it's at the beginning of a number, they're not significant. If they're at the end, they are significant if they're after a point. But if they are not after a point, you don't quite know if it's significant. That's why we have something called scientific notation. That's one of the reasons. The other one is to get rid of all these excess numbers. And so we would write this as a 2 if it wasn't significant, by 10 to the 1, 2, 3, 4, 5, by 10 to the minus 5. If it was significant, we'd write 1.38200 by 10 to the minus 5. Now that becomes after a decimal, we can see we now have 1, 2, 3, 4, 5, 6 significant figures instead of 4. Another way to write it is simply just to put a dot at the end here. I don't see that very often, but that is another way to do it. So here are some practice ones. Please stop the video and see if you can get these ones right. And here are the answers, so you can stop the video and see whether you got those right. Hopefully these explanations will lead you to the right answer if you got it wrong. Looking at how to do calculations now with your significant figures, there are two basic rules. The first rule is if you're multiplying or dividing, you take the least significant figure and you give that in your final answer. So it's all about doing truth, telling about truth. It's all about finding the weakest measuring instrument or measuring method, and that is as accurate as you're going to be. So that is the best truth you're going to give. So in here, this one's got 3, this one's got 4. So your final answer must be rounded off to 3 sig figs. Now if you have addition or subtraction, it's a little bit trickier. The best way that I can explain that, this took quite a long time to come up with this sentence, you should have the same number of unit placings as the most imprecise number. And I think this also gives sort of the spirit of the science that's involved here. You're looking at this here as the weakest, most imprecise instrument. So your final answer should only go up to the weakest, most imprecise. So that is 2 unit placings, so 2 hundredths instead of thousandths. Here, this is the most crude number, and this is far more precise. So then you must make your answer to that the most imprecise unit placing, which is there. So here are some numbers done for you already. Have a look at whether it's times or divide. All these ones are all times. So take the smallest sig fig and round them up to the nearest sig fig. Stop the video and see if you get the right answer. And hopefully you got these numbers. Alright, next is the addition and subtraction. I find it easier to draw lines where the most imprecise number is. Try this and see if you get it correct. So that's how I do it. I'd put a line there if I was having trouble. I don't actually do it that way, but this is just for teaching purposes. So you should have got the final answer is 58.9. Now try this one, see what you get. Pause the video. That's the answer, and one more. And hopefully you got that there. So this one here, it goes only down to the tenths. Alright, here are some more examples. So you can pause or skip. And here are the answers. Moving on to some more terms now. Absolute uncertainty and percentage uncertainty is to do with the actual values that you take. So if you took a reading of 1.0 plus or minus 0.5, the absolute uncertainty would be here. And the percentage uncertainty would be that value, that uncertainty divided by the whole number value of that, and that would be times by 100 to get a percentage value. The absolute error, on the other hand, is your final answer. So you do a calculation, you come to say 5 milligrams of vitamin C, and that's a lot, but anyway, and then you'll have some sort of measured value. Maybe you should have got 6 milligrams. So the percentage error would be 1 milligram difference, and that's divided by 6 milligrams. So they're quite confusing, those terms, because they overlap. So absolute uncertainty, absolute error, percent error, they're all quite different. So have a little bit of a think about those when you get questions on those, and you're going to have to use those in your experiments too. So here we have propagation of uncertainty, which you definitely need for your internal assessment, but will also be covered in multiple choice questions in your exam. How do you get the uncertainty of a value that you have, plus or minus 0.5, and perhaps some other sort of reading such as temperature? How would you get the uncertainty in your final calculations? So say if you use Q equals MC delta T. So the rules are, if you're adding and subtracting, that's the easiest. You just add the uncertainties together. And the more difficult one is if you're dividing or timesing, then you need to work out what the percentage uncertainties and you add those together. So let's have a look at an example. Here we have a data table. We have the uncertainties here, and we're going to do density. So I'm going to take the values from here. So have a flick back to here if you need to. So first of all, the mass of the beaker, that's just a plus or minus, a mass of the water, and we need to minus the mass of the beaker. So we've taken those values and we've minused them, and you'd come up with 10.3. Now that we have uncertainties, what we do is we just add those uncertainties together because it's a plus or minus calculation. So that is our answer that we're going to work with. We're not going to clean it up until we come to the very end. The next one is a little bit more difficult. Now that we have the mass of the water, we have to divide it by the volume of the water, and so this is a plus or minus, this is a times or divide problem, so we now can have to add the percentage uncertainties. So quite simply in the past you would have just done those two values divided by each other and come up with this value of 0.9833. Okay, so now you grab your uncertainty and divide it by the total value and you come up with these, and if you times it by 100%, that gives you the percentage, and so you get 0.05, so that's 5.9%. So you then grab that 5.9% and you times it by your final answer, and that will give you 0.05897. So you're almost done. You've managed to grab the uncertainty of a final calculation. The last thing you need to do is convert this here to 1 sig fig, and then once you've done that, so that would take you to 0.06. You then need to make sure that your value looks similar to your uncertainty, and so you take that to the same number of decimal places, so take that to the hundredths. So you need to get rid of these thousandths and round up or down accordingly, and that is the correct final answer. Now you have finished your calculations in your science report when you've done your uncertainty and propagation on your final value. That gives you an understanding of the random error of your experiment, and then the second thing you do when you're finally finished in most experiments is your percent error. So that will give you an idea of how your systemic problems, and then you can consider that finished and start working on your discussion to explain these things. So how do you do that? You need to reference a measured value or accepted value or a theoretical value. You may be working it out yourself, and so you minus that, minus those and divide it, and that will give you your percent error. So that is how accurate you are. Now make sure you use the words accuracy and precision, as well as random and systemic, the actual words, when you write up your discussion or give your answers in a test. So here is an example. Here we have a density here and the true value here. So we minus them from each other to get this value and divide it by what the answer should have been. And we take that, the absolute values here, we could take that down to a 1 sig fig, just to simplify it, just for communication, because that's not very clear, and also that's not realistic either. So the final answer is I'm 0.6% off, which is a little bit too good actually. Measuring with glassware is important. I've covered this in the topic you're going to do next, which is 1 stoichiometry. So I'm just going, you can listen to this or skip it. I'll just cut out a piece of video from there, or you can skip it when you listen to video 1. Just a quick overview now before I show you. Always rinse your analytical glassware with the solution you're going to use. That will help dilute out any impurities or get rid of any water or anything. It's better than rinsing it with anything else. So rinse it with what you're going to use. Make sure the meniscus always just touches the line where you need it to be, Make sure it's always vertical. Make sure this is a 45-degree angle, and make sure you leave it for 2 or 3 seconds. It's calibrated to have a little bit remaining in the tip, so that's fine. Similarly with your burette, rinse it with the solution you're going to use. Make sure there's no air bubbles there. Make sure the meniscus there, and most importantly, read it to half the smallest increment. The volumetric flask is a little bit trickier in that when you measure this here, you've got to get the remaining bits out. So you need to rinse that out with a water bottle. Rinse this bit out too. Make sure it's not full. Mix it first. Make sure it's dissolved first so that you can mix it thoroughly. Once it's thoroughly mixed, you can then top it up and fill it up with a pipette and do it to the meniscus. And that will be your standard solution.